Hello, good evening, and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. How's it going? Hope you all are having a good Tuesday, good start to your week. And looks like everything's working today, so can't complain too much. Made the mistake of touching something on, or told my BIOS to try to update, which means that it decided to update Windows. I was fortunately able to stop it before it decided to restart my computer 10 minutes before stream. It has been known to take over an hour to try to install this thing, and it doesn't work. So, hope everybody's doing alright. And I'm going to start by... There we go. Hopping into some... I mean, I should know better than to try to do this, but why not? Edwin Moyes, elementary geometry, just for a few minutes, because I know there's already two people here probably. I see you. Alright, so we already did Theorem 1 and Theorem 2. We talked about zero product property, which was if you have a product of two numbers a and b that equals 0, then either a has to be 0 or b has to be 0. So we know that that has to be the case. Theorem 3. Zero has no reciprocal. Alright, there is no number such that 0 times x is going to be equal to 1. Alright, so I'm thinking here that this is as easy as it looks. Alright, so the proof on this one is going to be just that 0 times x is going to be equal to 0. Yep. For all x in the real numbers. Therefore, in this particular case, we have that this stuff over here, 0 times x, would be equal to 0, which would need to be equal to 1. But by... we had something earlier. Right, okay. By Theorem 1, we had that any number times 0 is going to be equal to 0. And we had a really, really important thing that was back here. At least I thought it was. Okay. Which was that 1, there we go. 1 cannot be equal to 0. So due to the fact that 1 cannot be equal to 0, alright, 1 cannot be equal to 0. So, no such number could possibly exist. Alright, QED, I guess. So this explains why, at least in an algebraic sense, division by 0 cannot exist. All right. It's lagging a little bit. That's going to get distracting. All right, cancellation law of addition states that if A plus B is equal to A plus C, then B equals C. Okay, so we did something like this in Xena, where basically this is a left addition. So we're saying that we know that A plus B is equal to A plus C, so therefore we can be able, in this particular case, to add on the left a negative A. And then by association, we're going to take these two things together. And negative A plus A was equal to 0 plus B equals 0 plus C. And then here for both B and C, these are additive identities, so we do get B is equal to C. So additive inverses can be added to both sides. Right, cancellation law of multiplication states much the same as the other one. So if we have A times B is equal to A times C, then B is equal to C. So again, by much the same token, we're going to take A times B is equal to A times C. We're then going to left multiply both of these things by 1 over A, and then associate by the associative law of multiplication. And 1 over A times A is going to be equal to 1 times B is equal to 1 over A times A is 1 times C. And naturally by the multiplicative identities. In this case, we have B is equal to C. So, again, as was to be proved. Alright, theorem 6 says that negative A is going to be equal to A for all A in the real numbers. And in fact, we could probably extend this to complex as well, but we're not going to push it that far. We're just going to talk about real numbers for now. Okay, so a negative number is the additive inverse of the number in question. So by definition, we have right, negative A is going to be equal to some x value, which is the additive inverse of negative A. Which means, because of this, negative A plus whatever our x is has to be equal to 0, which then has to be the same as x plus negative A. Right, so negative A has to be defined by x. And in this case, we have already talked about in some of the previous stuff over there that negative numbers are in fact just inverses of positive numbers. Additive. And so therefore, since we already have negative A here, then the opposite of that is going to be A. So negative A parentheses plus A is equal to 0, which is equal to A plus negative A. So we have talked about this before as the additive inverse. So we talked about this back here somewhere. Yep, additive inverse. So here, negative r plus r is equal to r plus negative r is equal to 0. So here, same deal, just using a's. So therefore, a must be equal to x, and therefore, negative a is equal to a. I guess there's a little bit of a leap in logic here, which states that, or because the additive inverse states that there is only one. That one should not be a comma, that one should be a colon. Alright, there's only one possible additive inverse of any number r, and that is going to be negative r. And so negative a and positive a are going to be inverses of additive inverses of each other. I guess we could also do this if we talked about like multiplication of negative numbers. I'm not sure we did though. Yeah, not so much. But I was thinking here, alternate proof for this would be, for instance, that negative a is going to be equal to negative 1 multiplied by, parentheses, negative 1 times a. And then here we can reassociate as negative 1 times negative 1 times a. Now, I think that we might be stuck in this particular location because we don't technically have a definition of like multiply by negative 1 at this exact moment in time, but like, oh, yep, there it is. Theorem 8. Oops. All right, so for theorem 7, we had, parentheses, negative a times b is equal to negative parentheses a times b for all a and b in the real numbers. So if this is true, we have a property that involves negative parentheses a times b, and that would be that negative parentheses a times b plus a times b is going to be equal to 0, which is then equal to a times b plus negative parentheses a times b. Well then, can I explain directional derivative? So, I mean, that's... So yes, it's going to take a minute, of course, but... Uh-huh. Okay, yeah, yeah. So, so in this particular case, we're talking about using the del operator, which again, del of f on xyz is just going to be equal to the partial derivative with respect to x of f by, right, because this is going to be a vector, partial derivative with respect to y of f, comma, partial with respect to z of f. All right, so what we're looking at here is saying that we want it in a particular direction. So instead of choosing the gradient direction, so again, this is the direction of steepest, I mean, I usually say descent, but could technically be ascent then. Oh man. So yeah, the gradient direction, this is the gradient vector. So this is just your del f. Del f. So we get here the direction, again, is the partial derivatives of f of f along the directions x, comma y, comma z. So take each of those partial derivatives, and that'll get you the direction of steepest descent. All right. Then, if you want it in a particular direction, so let's say I want, what is the derivative of the function in this particular direction instead of in whichever direction is the steepest ascent or descent, then we're going to take this and say we're going to do the same del f that we did before with this stuff. However, we're then going to dot it with the u vector divided by the normal of the u vector. So this right here, all of this, right, u over norm u is going to be u hat. So this is the unit vector in the direction of u vector. So let's say you've got f of xyz is going to be equal to 3x squared y minus 8 z plus 4xz minus, let's do plus again, 5 yz squared, just cuz. Okay, so we've got this thing, and we want the directional derivative along vector 1, 2, 3, just cuz, right? From, because we can do that too. 4, 4, 4. Yeah. That's all right. Let's change this one to negative and see if that does anything. I'm trying to partially cancel stuff out, so it's not a gigantic number, but... So if we want the directional derivative along the vector 1, 2, 3 from the location 4, 4, 4, then we're going to take this and say we want del f dotted with, right, u vector over norm u. And then we need to make sure that this has the point 444 plugged into it at the end. Okay, so del f is going to be, no, that's a vector. Del f is going to be a vector denoted by the partial derivative of f with respect to x. So the first term is going to drop the 2 down. It's going to be 6xy. Okay, second term has no x's. Third term has an x. That's going to be minus 4z. Third term has no x's. Comma. First term has y's. It's going to be 3x squared. Second term, third term have no y's. Fourth term is going to be a plus 5z squared. Comma. Z's, we got none in the first term, negative 8 in the second, negative 4x in the third, and then a plus 10 yz in the last. Okay, dotted with the vector 1, 2, 3 divided by the norm, which is going to be the square root of 1 squared plus 2 squared plus 3 squared. Okay, 9 and 4 is 13 plus 1 is 14. So all this stuff multiplied by, it's going to be 1/14, root 14, not 14th, comma 2 over root 14, comma 3 over root 14. Dotted with, okay, these are all 4s, so all of our variables are going to have 4s plugged in for them. 5 and 3. Good evening. Welcome to NSimplex for Chicken. My name is Obi-Wan Pez. We're going to be doing some Calc 3 for the moment. Helping out one of our regular followers. Somebody who comes in every week. Thank you for your loyalty here, Blainley. And it's a good thing. Keeps me busy. Okay, so this is going to be... so this is an interesting one. We can shortcut this by noting that both 4 times 4 in both these cases are 16. So then this is going to be 6 16s minus 1 16, which is going to be 5 16s, which makes it 80. Comma. Here, we also have 16s to talk about, so we've got 3 and 5 of them. So that's 8 16s, which is going to be... 8 by 16. Alright, the other way to do this should be 128, right? Yeah, the other way to do this is we can multiply 8 times 8 times 2. So 64 by 2 is 128. Oh, doing pretty well. Thanks for asking. I got really excited in my pre-calc class today. I think some of my students were energized. Others were slightly amused, and others just plain left. I don't know that that's a reflection on me, but you know, sometimes it hurts. Never take it personally. Okay. So we got 10 16s here. We're subtracting 1. That's going to be 9 16s, which is 144 minus 8. It's going to be a 136. Dotted with 1 over root 14 by 2 over root 14 by 3 over root 14. Yes. Don't do that. Okay, there we go. I hit something. That was not fun. Yeah, so I teach math at a 2-year college in the Mid-Atlantic of the United States. And generally that's anywhere from like beginning algebra all the way up through differential equations. And my expertise is pretty much limited to teaching that stuff. I do, however, on the other hand, try to learn some other stuff, and I have, of course, taken math classes up through senior level linear algebra and master's level stuff. So I've done stuff. I don't necessarily remember all of it because it's been a while, but I try where I can to apply a bunch of the teaching methods that I have learned over the years to whatever anybody asks. All right, here it kind of depends. So like I'm more or less living my life in pre-calculus, because that's where I've taught the most, and as it turns out, I have taught the most classes out of anyone at my institution in pre-calc. Like compared to anyone on the roster, I have taught more pre-calc than anybody. Certainly the accelerated class that I teach, I have taught more than literally anybody on the entire roster. So I like to... It's only been 15 years. But you know, there are other people who have taught longer and probably have taught the single pre-calc classes longer. But you know, interestingly enough, no. Going into college, I thought I was going to be a theoretical astrophysicist because I have. Let's see. Nah, they're all at school. Um, my bookshelf at school has all of my actual books, but Skywatcher's Year, for example, I definitely thought that I was going to go into astronomy and astrophysics, preferably to study uh, my specialty that I was like trying to eventually get into was probably going to be black holes, which I'm kind of kicking myself that I didn't do more, given that we just discovered a whole crap ton of black holes and new methods of discovering them, and I was like, but I think I made the right choice. Not just because I'm here, right? I'm doing this. This is awesome. I'm teaching math. I'm doing all sorts of cool stuff. I've invented some interesting little tiny methods within pre-calc especially, and I've tried teaching, you know, new ways, new things, new connections that I'm making between subjects, and it's really cool. So it's not just that, but I think that like wherever I went, I probably would have figured something out pretty cool. Yeah, so like theoretical astrophysics is not like the math behind it would be really hard. So I go 2 streams a week. My Tuesday night streams are math, and I do homework help, whatever people want to talk about. Try to see if we can push the boundaries of what you know, that sort of stuff. And on Fridays, we just have a good time. So I've been streaming Elite Dangerous. I've been streaming lately Soma, because that's a freaking good game. And 136 is going to be 394.08 over square root of 14. I'll tell you what, though, as far as theoretical astrophysics goes, I got through basic physics 1 and 2, and I ran up against what I call the Great Wall of Thermo. Found out that my friends were all taking it the next semester when I was going to take it, naturally, as a physics major. The grand total of the pass rate of our thermodynamics class was 39%. I was like, I think maybe I just kind of like to read about physics. Alright, so Blainland, this is our example here. We took the directional derivative along the vector 1, 2, 3 from 4, 4, 4 with this particular function here. In order to get that, we take del f, which is going to be here, 6xy minus 4z, the partial derivative of f with respect to x, comma, 3x squared plus 5z squared, which is the partial derivative with respect to y, comma, negative 8 minus 4x plus 10yz, which is the partial derivative with respect to z. Then we dotted that with u divided by norm u, which is again going to shrink this thing down so that we get a Pythagorean identity between these values 1, 2, and 3. So the Pythagorean identity shrinks it down to a unit vector, 1 over the square root of 14 by 2 over the square root of 14 by 3 over the square root of 14. When we dot that with the values that we plug in, again, x, y, and z are all 4, for better, for worse, we end up with the vector 80, 128, 136, dotted with the unit vector that we had here. And then when we dot those, we're multiplying 80 by 1 over root 14, 128 by 2 over root 14, and 136 by 3 over root 14. Now check me on that, but I'm pretty sure that's right. So Ivan, what are you learning these days? Occasionally I'll lean into this dead spot that's right about here, give or take. It's going to work now? Of course it is. Whatever. It's so weird. I contacted Corsair about this because I'm like, look, I've hooked in the thing on the back side of my computer, and just for whatever reason, like right here, right about here, I hit this dead spot. And they're like, yeah, it's so weird, it shouldn't do that. I'm like, thanks. Pretty sure I'm studying CS. Okay, no, I get you. Any current math classes that you're in, or just kind of like getting gen eds and prereqs out of the way? I'm sorry, I moved the connective. I read that the other way. You're correct. I'm pretty sure I'm studying CS. Oh man, it's been a long week already. So Blaine, then going back to your questions from earlier, that directional derivative is again going to be this del in the direction of u, or sub u, of f, which again is this process that we came through here. The gradient vector is just del f, with nothing else attached to it. Again, this is the steepest decline, so it'll show you what direction that steepest decline is. Alright, then your third question, conservation of energy. Ooh. Yep, that's a nice combo. So linear algebra, differential equations, and multivariate calc was my 3 that I took as a sophomore. That was it was in my experience, it was all 3 of them at the same time, and as one 6-credit class for 2 semesters. So it was heavy. I also managed to get mono during my second semester of it, so I failed it. Or, well, I got D, so. I think probably linear algebra I found the toughest. Differential equations and Calc 3 were enough calculus that it could just, like, just made me kind of appreciate what was going on there, and I'm good with algebra, so I can just move stuff around, manipulate it. Give me the rules, I'll figure it out. Especially back in those days. Linear algebra was just a different kind of thing. It was a different animal. Like, I just couldn't figure it out quite the same as everything else. Absolutely. Go for it. So in terms of conservation of energy, all of the forces or the energy is going to transfer between types. So your gravitational potential energy, wherever you have it, is almost exclusively going to transfer into kinetic energy and friction heat, so thermal energy in some way, shape, or form. Again, almost exclusively. And this also works for, like, chemistry. You have this, like, chemical energy. Oh, anything you want. I'll try my best. I also took, like, a graph theory light course in Masters as combinatorics. So it was like graph theory and combinatorics together. Oh, sure. So gravitational potential energy will convert into, like, kinetic energy and friction or thermal energy. You've got chemical potential, which will convert into reagents and reactants. Those are sort of the same thing. Resultant. Resultant compounds plus thermal energy. And again, there's all sorts of stuff, redox reactions and whatnot. I'm not, like, super great with chemistry in particular, but, you know, it was never really, like, I can balance equations. But I won't necessarily be able to figure out what, you know, aspirin will break into when it gets into your body, that kind of thing. It's just not my game. So the conservation of energy, you just have to watch out what is the sum of all of the energy types, and it should be the same as the total energy that you had at the very beginning. And without more specifics, I probably won't be able to give you much else. installer that's like gone rogue on me. I was trying to install something. And it screwed up. Which, honestly, not surprising. There it goes. All right. I hope I didn't just kill something. Oop. It's yelling at me. Okay, I do not know what nilpotent means, but that is going to be easy enough to look up. So, A and B are both n by n matrices. Let C be equal to AB minus BA. If AC equals, oops, nope, CA, then C almost. Ooh, ew. There we go. Interesting. Product of the matrix with itself is going to be equal to a null matrix. Interesting. Okay, so C is also going to be n by n. It's not equal to. Alright, such that C times C is going to be equal to n by n zeros. This is not necessarily how you write things, but whatever, it's fine. That is not what that says. Interesting. X times r equals 0 for some positive integer r. Oh. Do that. Come. Ah, that's what it is. It's raised to a power, not necessarily. Okay, where K is the degree of nilpotency. I get it now. Okay. So we know that AC is going to be equal to CA. Okay. So let's go about it this way. We already know that C looks like this. So let's plug it in here. We know that A times C equals C times A. That's behind my face. Almost. There. Last time I did serious linear algebra was probably during my master's program. So that was 10 some odd 12 years ago. Now, granted, right, I've done some linear algebra since then. It's just not for a class. Never heard about nilpotency, or at least... I also took a matrix theory class, but I didn't really do well in it, so... I don't think it's terribly difficult. So here, I think if you start with AC equals CA, and then plug in C for these bits, AB minus BA for these bits, I think that it'll kind of come out. So this is going to be A times left multiplication, A times B minus B times A is equal to C, no, don't have C anymore. going to be association A times B minus B times A, right multiplied by A. So then this is going to be associative A times B minus A times B times A. It's going to be equal to A times B times A minus B times A times A. Okay. So, like, I don't necessarily know where to go from here, but if this is true, this also means we might be able to say this if we swap these two here. This is going to be a minus A times B times A. And this would be an A times B times A minus B times A times A. Now, I'm not sure that that's, like I said, necessarily going to do anything, but I think, at least to me, it seems like this is getting somewhere. May not be, but that dead spot again. It's right here. Right in here. Yeah, drives me nuts. All right. So the only thing we've really managed to do here is replace C with BA on this side and replace C with AB on this side, but that doesn't do anything. The other option is to attempt, probably going to be gross, but attempt to do attempt to do something like this and see if we can't do induction to show that it's going to work for any n value or k value. Or introduce A and C as large matrices. Hmm. Okay. So like AC be equal to A11, A12, to A1N, A21, A22, A2N, dot down, diagonal, ANN, AN1, AN2, by C11, C12, C1N, C2N, CNN, CN2, CN1. C21, C22. That's a C2N. Okay. So if we multiply these together, this is going to get that row 1 is going to be multiplied by column 1, point-wise. So A11 by C11. Plus A12 by C21 plus A13 by C31 plus out 2 A1N by CN1. Alright, and then this is going to be in spot number 1, which has to then be equal to CA, which is going to be the other way around. So this is going to be row 1, C11, A11 plus C12, A21. C13, A31, all the way out to C1N, AM1. The sums all have to be the same. It's not necessarily that any point-wise multiplication needs to be the same, for what that's worth. Or potentially write C11 squared plus C12 by C21 plus C13 by C31 plus out 2 C1N by CM1. And again, this is in slot number 1. So then you go over 1 or down 1. Thank you, Ivan. Important both to hydrate and get the coffee off of your teeth, because goodness, it's been staying on there pretty much all day long. Yeah, this is probably not going to be nice in any way, shape, or form. So. Okay, there's got to be a nice, easy way to get this done, right? I don't think they would make you go through, like, steps of having all sigma notation inside of a matrix. It just get really gross. I take it you've seen multiple then. Alternatively, could do it symbolically. I'm not saying this is nice either. Yep. Oh. Wait. Yep. No, not just... No, I literally just factored it backwards. That's just gonna get me... Yeah, okay. I only know a few Key and Peele sketches, particularly, the substitute teacher one. Ones, I suppose. Right, this is literally back factoring, so that's not gonna help. All depends. Mike, got anything else? Okay, so that's kind of fun. This could also be associativity, change, just AB by A minus BA by A. This is just C times A again. Just exchanged where this was in the grand scheme of things. Yeah, it's the same thing. Gun Center, how's it going? New friend came in. Asked if we could solve a linear algebra problem. And so far I have discovered the meaning of nilpotency. And then been faffing around, I suppose, is a decent term for it. So trying to determine if there's any way forward in figuring out if AC is equal to CA and C is equal to AB minus BA, then C is going to be nilpotent. So where C is n by n, C raised to the k power is going to be some n by n matrix for some, yeah. So far we took AC equals CA and replaced C with AB minus BA, and then tried to do some algebra with it. Didn't get very far. I shifted two of the terms around, but realistically this is the same as just doing associativity on both of those terms. So nothing really is moving us forward here. If you got any ideas, let me know. Just prod in the right direction. So far here, we've kind of got the same pattern for C that we've got in A's and B's, but that doesn't really help, right? There, we could say that there's some other matrix D that has this property or whatever, but I don't think it's going to do anything for us. Anybody else been up to anything interesting tonight? Yeah, Ivan. Hey, Superbrain. How's it going? Ivan, if you want to give me a prod here, I'll be okay with that. How's it going, Superbrain? Good morning. Still is not a reasonable time for you. It's really too bad. Here it is 10:30 at night. We just did our time change thing, so it's still feeling like 11:30. Only been at it for a couple of nights here. Not like I sleep anyway. Mm-hmm. So we only go halfway. Wait. I see. Yeah, because that's just proving the assumption. Right, that AC is equal to CA is going to be equal to... Oh, wait. No, right. Recreational math. Yes. Always fun. Right, so we won't necessarily be able to prove that commutativity works for any particular or for any generalized matrix. We can do it for any particular matrix. But I don't know that we can do it for just a generic A and B, which should, again, be probably fairly helpful. So Blainland, inertia, just as a concept, is the uh, resistance to an object to change its um, position and velocity. So it's like a resistive force to its acceleration. Maybe. Yep. F sine theta is equal to I plus mr squared. So that is that appears to be something related to moment of inertia, but something distinctly different about this. I don't have any I plus mr squareds anywhere. Oh god, was that thing we were working on before? The horse pulling at an angle. What the hell's that? Yeah, there we go. This might have something to do with it. Sort of slash not really. That's also cosines, not sines. Okay. So a sphere is rolling down an incline. Cool. Come on. Hey. this is going to have angular inertia. It's also going to have the moment of inertia. Yeah. There is unfortunately quite a lot to get through. I'm having a very similar problem in pre-calc, so it is kind of crazy. That's normal to this surface, this is normal to that. So, alright, have a good night, Evan. Good luck. No, I haven't like listened to Paramore in a while, come to think of it. Alright, so the inertia of 2/5 mr squared is coming from the inertia for a sphere. This is solid sphere. And then you said that you're adding you're adding mr squared. Maybe. Are we always just talking about sort of, no. It's like we might be thinking about it as like a hoop or something like that, but it's not though. Right? So the moment of inertia for a shell just mr squared is going to be either the hoop or simple shell. So this is going around. You could think of it like as a hollowed out, not a hollowed out sphere because that's different, but just like the strip of that sphere that's around the center. Hoop is really the best we can do there anyway. Alright, so then let's pivot the point in the incline. We're going to get normal force. Yeah. So, right. Yeah, I gotcha. So yeah, it works well enough at least to be a cylindrical shell. This is what's really weirding me out though. So you've got the inertia equation for the solid sphere. And then you've got the inertia equation for a hoop. And then that's it. There's nothing else here. Now I'm kind of curious. What would a series of individual shells get you for the sphere? Okay, so this whole thing here. Any one thing. Yeah, that's what I'm thinking. I don't know if it's just the shells, like the sphere part is kind of its own bit, and then the individual just outer rims of this thing is going to be the rotational inertia. So I'm trying to figure out. It's going to be the integral from right 0 to r. No. All right. I'm losing it here. Okay, so this is the end product of it, not the beginning. Give me a minute here. was looking like the sound was coming through even with this off for a second. I don't know. It looked... Anyway. Trace. Sum of the elements in the main diagonal. Okay. Yeah. Traces the sum of its complex eigenvalues. Sorry, looking at something real quick down here. Figure out. AB? Right, because you can get the Jordan form of the matrix based on the eigenvalues. Right, they have to be in the diagonal. Get a diagonalizable matrix, provided that that matrix is not singular. Hmm. Uh-huh. Should have guessed that. All right. In theory, yes. So, oh, uh, right? Because if, where the hell are we? Okay. If C is equal to AB minus BA, then both parts of the diagonal are here, and they're the individual multiplications of the diagonal stuff are commutative. So one minus the other is going to get us zeros for those things. Boo. Alright. That's just the easiest way to do it. That's not necessarily the right way. Yeah. Alright. I think I'm getting too tired for this too. Oh man. So the inertia for any one particular piece, right? It's gonna have to be larg. All right. Have a good night. I could probably use some spicy salsa. I've got some Indian red chili sauce and some Korean gochujang in the fridge that I've been regularly just like pouring into my salsa. Give it a little extra boost. Those are some fun times. Not at the same time. Oh, and then I've been getting what's his name? Greedo? I mean, it's not spelled the same as the character from Star Wars, but I think it's Greedo, Grido or something like that. Greedo's pickles, which come from Boston. This guy used to be like in a pushcart selling pickles on the street, and then they started selling them in containers in the store. And they come in two varieties, the standard and then the hot. So I usually have one of each on hand. The regulars are pretty good. The hot ones have sliced, thinly sliced jalapenos and habaneros like stuffed in there, and then a ton of garlic. Yeah. I was looking for them, and I went into this other food store, and they had those, or they didn't have those, so I was like, all right, let's get another one. So I got some that were like, you know, New York's finest or something. I don't know. It had like, you know, Statue of Liberty on it, and I was like, I don't know. And then I looked at the top of it, and like the pickles look all clear, somewhat translucent. I'm like, I don't like the look of that. I was desperate enough to buy one that looked like sort of okay, and I bit into it and it was just mush. I'm like, no, nope. So I finally went back and got the Greedos ones. Way better. Snappy. Oh no. Yeah. Yep. I was very sad that I had bought those. Oh well. Alright, well, thanks everybody for stopping in. I'm gonna probably get off here and maybe actually get some sleep. We'll see how it goes. So, we're gonna go over and raid. It's Tuesday. we gonna see today? Huh. Okay, so let's go see Selena. She's had she's been playing Super Metroid. It looks like she might be doing a Super Metroid and a Link to the Past randomizer. So that looks nuts. Yeah, and she's also got like a strong Kirby. We will see how it goes. Yeah, my brother is actually a speedrunner in Super Metroid. He's been working on some crazy exploits. Maybe I'll introduce him at some point, but at any rate, thanks everybody for stopping in. I'll see you on Friday for some game stuff. We're gonna maybe do Soma. I don't know. I'm being chased around a small area. I don't like it very much. So maybe we'll try something else for a little bit. Try and work it out off stream or something. I don't know. I'll figure it out. Anyway, and next Wednesday for more math stuff. So, have a good week. See you all later. This is Obi-Wan Pez for Unsimple Pachinko. Have a good night.